Who had question 6? Who's question 6? Oh, you guys have the longer one. I'll jump in there too. I'll explain the other two. Okay. Okay. Yeah, so I said, look in your notes, look in your simulation.
KMT PowerPoint.
All right, thumbs up when you're ready. Generally ready. If not, you have to improv a little bit. All right, well, we're going to start regardless because this is something that you've seen a couple days in a row now, so this is a recap of everything KMT related. All right, so stand up. Question 1. Let's go. Stand up at your seat. Stand up in the front. Stand up wherever. Not on like top of the desk or something, but stand up. Stand up. You too. Yeah, your question 1. Okay, if you do not know one of these, then jot down a quick answer about it. But this is kind of the conceptual stuff that you would be expected to on the on the multiple choice part of the test. Okay, conceptual. Go. What's KMT?
KMT is a kinetic molecular theory, which means that within a sample of particles, not all particles have the same kinetic energy, and the average kinetic energy is proportional to the temperature.
Okay, so it's a theory that's used for what though? To explain what?
How particles move.
Okay, in relation to real gases versus ideal gases. All right, cool. Question 2. Tell me the postulates, which are the details of the kinetic molecular theory. They're like 3, 4, maybe a couple more. It depends on how detailed you took the notes. It's okay. Just go for it.
Volume of a gas arises from the space between gas molecules.
True.
Particles are in constant motion.
True.
Particles are assumed to exert no forces on each other.
True.
And average kinetic energy is directly proportional to intelligence.
Okay, is there one of these down here that nobody has the kinetic energy equation? What are the kinetic energy equations? Anybody? RT on top, okay, so 3/2 RT. Okay, that's average kinetic energy. What else? There's another one. This one's like if you're given a sample of gas all at the same temperature. 1/2 mv squared. Okay, this one right here is for one particle. It's for an individual gas particle because you're considering the mass of that individual gas particle and its own velocity. But this one over here is for a whole sample. So an entire sample, you're not specifying one mass or one particular particle. You're saying at this temperature, this sample of gas particles should have this average kinetic energy. This one's going to give you a bit more specific information. Okay, so that's included there. And then I had lots of things I wanted to add. You said no. You assumed they have no interactions, right?
Yeah.
Yeah. Okay. And okay, that's good actually. Okay. Number 3, stand up. Why is it safe to assume gas particles' size does not make a difference when measuring the volume of a gas?
We said because the collision of molecules against the surface makes a difference in volume. No.
And there's too much space in between the particles to assume that that's the actual volume. It's just they're bouncing around and they make sense.
Okay, so the volume of gas particles is negligible. That's kind of the simplest statement we can say. The volume of gas particles are negligible, which means we assume the volume of the container is the volume that they have to move around in, even though we know for sure they actually do take up a minuscule part of the volume. But they are colliding and bouncing around. But that doesn't have a whole lot to do with volume. It's like just the volume they make up versus the volume total. Okay, what is true of 2 gas particles at the same temperature?
The lighter one diffuses faster.
Okay, so same temperature means they have the same, right? So first of all, they have the same kinetic energy, and then you said if I have 2 different gas particles, one's heavier, one is lighter, then you know what about its velocity?
The lighter one's faster.
Right, and the reason that works is because whenever you have this kinetic energy equation, 1 half mv squared, if both of them have to equal the kinetic energy, whatever you calculated, then if one is bigger, the velocity has to go down because it's indirectly related. Okay, question 5.
Okay, so the collision of one gas particle with another is completely elastic because the particles don't stick together.
And so what happens to the energy when they collide?
It is conserved between the two bodies, and then inelastic is kinetic energy is not conserved, so when the two bodies collide, it will still.
And so energy can be transferred to one, but in a lesser amount. So like you guys can imagine if two gas particles hit each other, they can bounce back with the same amount of energy. That would be considered elastic collisions. If they collide with each other, one bounces with a little bit more energy and one bounces with less, there might be energy loss in the process. So elastic collisions is generally what we assume for ideal gases. All right, 6, use the KMT to explain Boyle's and Charles's, and then I'll do the other.
Okay. Boyle's law is pressure and volume.
And as you decrease the volume, the collisions increase, which increases
The collisions of the container wall specifically, right? Okay, so.
And then Boyle's law is temperature and volume, and they're directly related, so they go up with each other and go down with each other.
Mm-hmm.
So like say you have a piston and you heat up the gas inside, then the volume's going to expand and the piston's going to go up. Because what's staying constant with Charles's law? The volume. You said the volume and temperature. The pressure. So the pressure has to stay constant. So if you heat up the particles, they're doing what with container wall? Colliding
More frequently and with more force. So there's two sides of this sword, okay? So you mentioned whenever you talk about temperature, you must say they increase the frequency of collision and increase the force of collision, which would do what to your pressure? Would do what? It would increase pressure. No, we can't do that. So what do we do instead? Increase the volume to counter that tendency to increase the pressure, because Charles' law said you can't do that. Cool. And then Avogadro's, this one's a relationship between what and what? What two variables? Moles and volume. Okay, so if you increase the number, if you have a container, you increase the moles, automatically there's more collision, so what happens? What? I'm not there yet. So if I increase the number of particles in a standard a set container, what happens? Okay, so more collisions means more pressure, right? Well, I can't have more pressure. I have to therefore counter that by increasing the volume. There's a reason why we say there's correlation. It's really due to pressure. You have to talk about collisions all the time. And then Dalton's law is just the summation of partial pressure, so P1 plus P2 plus P3. So this one basically states the identity of the particle is irrelevant. It's the number of collisions of the container that would sum to equal the total pressure. So if I have, a big gas, a little gas, a big gas, it doesn't matter. The identity, it's their collisions with the container wall. That sum to be equal to total pressure. Okay, 7. In a mixture of gas at the same temperature, how are the masses of the gases related to their velocities? 7?
Particles with a greater mass will have a slower velocity because they're bigger.
Okay, and?
A smaller mass will be a faster velocity.
Okay, what about their kinetic energies?
They'll still be the same.
Still be the same regardless of their size. Right, cool. Draw a diagram, page number 8. Can you draw me a diagram?
Sure, I thought maybe we just described it. You would?
Okay, you can describe whatever you need to do, but you can also tell me the axes and exactly what it looks like.
Oh, okay. So x-axis is velocity. Y-axis is number of particles.
Meters per second, she said, yes. Number of particles.
And then further to the right is higher temperature. Like if there were a curve.
What's that curve look like? Just draw it for me. Okay, so one goes here. Give me a colder temperature curve.
Like at the tallest.
So where's the max? Where's the maximum speed? This far?
No.
So like here. Okay, so if you looked at a graph like this, you would be able to tell me the one that has the farther range or the bigger range of speeds means it has the higher temperature, because higher temperatures means you have lots of speeds available because you have a very, very high amount of kinetic energy, versus this one would be a lower temperature because it's going to max you out at a fairly low kinetic energy because you have a low, because of the relationship between kinetic energy and temperature. And so even with this information, let's say this is the same, this might be the same gas, at two different temperatures. So what can you assume about the volume, the area under the curve here and the area under the curve here? Area under the, have I said anything about changing the amount of gas? I just changed the temperatures, right? So you assume that the area under this curve equals the area under this curve, even though it's not really to scale here, because the number of particles are consistent. It's just that these are moving faster because there's a higher maximum temperature. Okay. 9. What's the equation for the root mean square? Root mean square velocity of a collection of gas particles.
Square root of 3RT over M.
So what's this called? What's the symbol variable for?
U and then
Erms.
yeah.
U erms.
Square root 3RT over M.
In what unit? Kilograms. Cool. And that's going to be measured. What units would this deliver if you kind of had to do your whole assumption what joules meant?
Meters per second.
Meters per second. Yeah. Okay. Cool. That's a quick review. What about these questions? Oops, not here. These questions here. I want to do some of these. These are the ones that we didn't get to review on Friday. So 1 through 7. I have my key that I can read from here. I've got 2 different keys. I think I did it 2 different ways between the many years of me making these keys. So tell me what you guys got for number 1 here, for the average kinetic energy. Ooh, this is the wrong. This is right, okay. Tell me what you guys got for the average kinetic energy of methane at 271 Kelvin. Shout it out. 3,380. 3,380 what? Joules per mole, because that's the only unit that doesn't cancel. And then you can just assume that the higher temperature is going to have a higher amount of kinetic energy. I'm not going to do every single one. What equation did you use? Kinetic energy is equal to 3/2 RT. R is the 8.314 joules per mole K. Kelvin is in Kelvin. Temperature is in Kelvin. Okay, so if you had to do the root, I don't know why I put root mean square velocity for that same story. You're using the root mean square velocity, square root 3/2 RT over M. But what was your M value for methane? Okay, so you added up, you moved the decimal back 3 to get the kilograms, 0.016 kilograms per mole. Okay, calculate, I'm sorry, this one right here. Number 3, the diffusion rate of an unknown gas is measured and found to be 31.5 milliliters per minute. Under identical experimental conditions, the diffusion rate of oxygen is found to be 30.50. If the choices were blah, 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 what's the identity of the gas? How did you guys approach this one? I might need another page here. So you had 31.50 milliliters per minute. You had 30.50 milliliters per minute. You knew this one was oxygen gas and this was unknown. What equation? There's only a couple of equations, right? I'm not going to say a couple. There's quite a few gases, but there's only one that relates to rates, comparative rates. Which one?
Rates over rate equals more than that. Square root of more than that.
Okay. So now you got to tell me which is which, right? So I told you the hint on how to make a kind of a number that makes sense. Which of these is the lighter gas? So which one's traveling faster? Which one's diffusing faster? X is diffusing faster because more of it's being released per minute than the oxygen per minute. So this one's going to go on top because the lighter one goes on top, the heavier one goes on bottom. So then it goes here, denominator. X because you don't know the molar mass of that, but you do know oxygen, which is what? 32 grams per mole. So the rate over the rate is 31. I'm just going to write this again. 31.5 over 30.5. So tell me how to solve. Okay. So 32 over x is equal to, what is this? This 1.0327 squared. Okay. I don't have that number. I just usually don't. I keep my calculations to a minimum. So then what do you do here? how do you solve for x? So do 32 divided by this guy equals x. So you guys have your calculator out. And remember this is in grams per mole, so x is going to be in grams per mole when we get there. Whenever you're ready. 0.005 grams per mole. Okay, so of those gases that were, let's see here, methane, carbon monoxide, nitrogen monoxide, carbon dioxide, and nitrogen dioxide, which of those is 30 grams per mole? Nitrogen monoxide. So 14 plus 16 is 30, so that will be our identity. You'll have one like that on your free response for sure. Identifying an unknown gas like that. Okay, so one way of separating isotopes is by diffusion of carbon monoxide. So it's just simply carbon monoxide diffusing, but we have different isotopes of oxygen embedded in that carbon monoxide. So you can see like we went from carbon 16 to carbon 17 to carbon 18. So what's really different between those molecules? What oxygen, which makes what different about the molecules there? The mass. So this one weighs 28 grams per mole, 29 grams per mole, and 30 grams per mole. So those masses make them effuse at different rates, which would therefore allow for separation of the gases simply because one is effusing faster than the other. So we could easily do the relative rates of those where you compare like 28 grams per mole over 29 grams, or 28 over 29 flipped actually whenever you do your relative rates with the rate A over rate B. But what would be an advantage of separating oxygen isotopes this way versus with carbon dioxide? So before you can really answer that question, what's the main difference between carbon monoxide and carbon dioxide? What are some of them? Okay, so mass is different. What else is different? What's carbon monoxide look like in a Lewis dot structure? C bonded to O. I believe it's a double bond like that. I think that was it's close, right? So this one is polar, non-polar. Carbon and oxygen, who's more electronegative? Oxygen's more electronegative, so this one is going to have a dipole moment pointing this way. This is partially negative, this is partially positive. So if there's an area where there's more electrons than another, there's unequal distribution of electrons, that means this is polar. Okay, so that therefore it's going to interact with other carbon monoxides quite a bit through dipole-dipole interactions. Carbon dioxide looks like what? Okay. What did you conclude about its polarity? It's non-polar because we have a carbon dipole from carbon to oxygen pointing in opposite directions. So what happens to the dipole moments? They cancel, so neither side has more electrons than another, so therefore it's non-polar. And what kind of IMFs are those? One dispersion forces, this was dipole-dipole forces. So one thing to consider is the polarity, because these right here, these carbon monoxides, are actually going to interact with other carbon monoxides, which might make it difficult to diffuse because they're attracted to each other. So they're going to stay stuck together. Whereas carbon dioxide might actually be an advantage because it's going to not have as much attraction, so it might cause more separation. However, these are lighter, so they still might diffuse faster than these. So that's why it says advantages and disadvantages. As long as you mention something about the polarity of it, you're probably good. You just have to recognize what they're actually asking for. Because sometimes you're like, what is this question? But it's more based on the chemistry behind it. Okay. How about 5? How did you guys approach 5? It took 4.5 minutes for a liter of helium to fuse through a porous barrier. How long will it take for a liter of chlorine gas under the same conditions? Rate over rate. So who is the top rate? Helium because it's lighter, chlorine because it's heavier. Okay, so then what did you put in your fraction here? Not a molar mass yet. Well, we can actually go. We'll handle the 4.5 thing up again actually. So what did you put in here? 70.9 grams per mole over 4 grams per mole, which is the mass of each, and then that number Thank you. 4.21. This O. What is the significance of that number? Describe it. Say it. Use that in a sentence and tell me what's actually. What does it relate to? Okay, so helium is 4.21 times faster than chlorine. Okay, so then what does that mean in reference to the 4.5 minutes? Or how would you figure out how long it took for chlorine to travel? That, or the liter of it to use. You just multiply. You say, okay, so 4.21 times faster is the rate, and you're multiplying that by the 4.5 minutes to give you, thank you, about 19 minutes is the time it's going to take for chlorine gas to travel, that 1 liter of it to a fuse, versus the helium. And that makes sense because it should be a lot slower, so it's going to take some time for it to travel, or to fuse. And then, oh, this is the GMAS method. Whenever you have, you guys don't know how I pronounce that to myself when I first read this. Whenever you have a compound, a hydrocarbon, some sort of organic compound, and it kind of tells you the process of what's happening here. But that part really doesn't matter. It's the information about the compound at the very end. So you have a 0.253 sample of the compound. That's this compound here. You have it producing that volume of nitrogen gas with saturated in water with a total pressure being 726 torr, and then I finally ask you for the mass percent of the nitrogen in the compound. Well, before we can get to mass percent, what information do you think we need? What would you use to calculate mass percent of nitrogen? Okay, so we have total mass rate, so that's going to go on bottom, 0.253 grams total. What's going to go on top? Yeah, grams of nitrogen. So our question is, what are the grams of nitrogen? And then we would times that by 100 to get to the percent nitrogen. So before we can get to grams of nitrogen, what do you think we should get to before grams? Moles of nitrogen. Okay, so if you're thinking N for moles of nitrogen, and you're given a volume, you're given a total pressure, but you also are given the water partial pressure. You kind of have P, you have T, you have V. You're going to solve for N. So what equation? What equation, people? PV is an RT. So I'll set this up for you, but PV equals an RT when you're solving for N. The P, though, is given to you as torr, and then you're also given the water pressure, or water vapor pressure, so what do you do first? So subtract the water vapor pressure, and then convert to atmospheres. That's going to be the P of nitrogen, and then the volume would have to be converted to liters, and the temperature would have to be converted to Kelvin, plug, plug, plug. You find N for moles, and then convert to nitrogen with its molar mass of what? Molar mass of nitrogen, 28 grams per mole. Okay, so I'm not going to do the whole problem for you right now. Okay, and then number 7, I did not tell you the values here. This is actually in your textbook. But if you have these gases here, so hydrogen gas, carbon dioxide, nitrogen, and methane, predict which would have the strongest IMFs. What do you notice about each of these if you think about their Lewis dot structures? Polar or nonpolar? Say again? Okay, but in all, they're all nonpolar, right? Because we have H2, it's equal on both sides. Carbon dioxide, which we just drew, was canceling of the dipole moments. Nitrogen is equal on both sides, and methane is a tetrahedron. So overall, C to H bonds are equal everywhere, so it's all nonpolar. So the polarity part is irrelevant, kind of. A or B, which of those variables relate to the IMFs? You got a 50-50 chance here. A, attraction. I want you just, because if you have to explain this, if you remember A means attraction, it's the level of attraction, which just relates to the IMFs of the particular compound. So if you remember A means attraction, the A value here is probably all going to be somewhat similar. What IMF do each of these undergo? They're all nonpolar. Which of the IMFs is relevant here? London dispersion. Of each of these, London dispersion is going to be stronger on one of them than others, and it's based off the mass. Well, what does B relate to? In the real gas formula, real gas laws. Van der Waals equation. You have the Van der Waals equation in front of you someplace? It relates to volume, which relates directly to mass. Bigger molecules have larger volume, meaning they have a higher mass. So of all of these, who would have the most interactions or the strongest intermolecular forces based off mass? CO2, because it weighs 44 grams per mole versus 2 grams per mole versus 28 grams per mole versus 16 grams per mole. So then the carbon dioxide would kind of default to be the strongest ion mass because its mass is the greatest. So it has the highest level of attraction. And it's the biggest, so therefore it has less space to move around, so naturally to start to interact more. Okay, so that's it for me for now. Okay, so I needed to review all those with you because those are the trickier. Out of everything gas laws, this is the trickiest. You guys have about 30 minutes-ish to work on your textbook problems, which are, I can put up back up on the board, or in your lab. Okay? 1 second. I still have your stuff. Yeah, I'll give you a second. So I'll pull up the textbook problems just in case you forgot what they are. What'd you say? I'm gonna come and see it as soon as I can. I need to look over your AP questions first. What AP questions? Okay. Here are the textbook questions, 73, 75, blah blah blah. You guys can read that. And I gotta change homework a little bit because we're not doing specifically a lab tomorrow. What is that? Okay, work. Work on textbooks or work on labs? Can you give this back to me at the end of class? Diamond, will you give this back to me at the end of class?
What's this? Oh.